Imagine this. You're looking up at the night sky on March 2026, and something extraordinary is happening. 3IATLAS, that ancient wanderer from another star system, is approaching Jupiter. But instead of sailing past our solar system's giant and disappearing forever into the cosmic dark, something unprecedented occurs. Jupiter's immense gravity catches hold of this interstellar visitor and whips it around, sending it hurtling back toward the inner solar system, back toward us. Tonight we're going to dive deep into what would happen if this 7 to 11 billion-year-old time capsule from the thick disk of our galaxy suddenly changed course and headed straight for Earth. Let's get started. So what makes this what-if scenario so fascinating? Well, 3IATLAS isn't just any ordinary comet. When it was discovered by the Atlas survey system in Chile on July 1, 2025, astronomers quickly realized they were looking at something truly extraordinary. This wasn't a local resident of our solar system. This was a visitor from deep space, carrying with it the chemical fingerprints of a star system that might have died billions of years before our Sun was even born. The James Webb Space Telescope revealed that 3IATLAS has a carbon dioxide to water ratio that's 8 times higher than any comet we've seen in our solar system. The Very Large Telescope detected atomic nickel vapor at temperatures where that should be impossible. And Hubble captured images of wobbling jets that tell us this ancient nucleus is tumbling through space in a complex rotation every 15.5 hours. But here's where our story takes a dramatic turn. In our hypothetical scenario, as 3IATLAS approaches Jupiter in March 2026, it doesn't just sail by at a safe distance of 53.4 million kilometers as predicted. Instead, imagine that tiny variations in its outgassing, those jets of carbon dioxide and other gases acting like miniature rocket engines, nudge its trajectory just slightly. Just enough to bring it within Jupiter's Hill sphere, that invisible boundary where the giant planet's gravity begins to dominate. And that's when everything changes. Jupiter, with a mass 318 times that of Earth, doesn't just influence 3IATLAS, it captures it. The comet swings around the giant planet in what astronomers call a gravitational slingshot. But instead of being flung further out into space, it gets redirected back toward the inner solar system, back toward us. Now, if you're feeling a chill run down your spine right about now, that's completely understandable. The idea of an interstellar object being redirected toward Earth sounds like the plot of a disaster movie. But here's the thing about science, and this is something I want you to remember throughout this journey we're taking together. Understanding these scenarios, even the scary ones, is how we prepare for the real universe we live in. So what exactly happens when 3IATLAS encounters Jupiter in our hypothetical scenario? To understand this, we need to dive into one of the most elegant and powerful phenomena in celestial mechanics, the gravitational slingshot. Picture Jupiter as a cosmic pinball bumper, but one with rules written by Einstein himself. As 3IATLAS approaches the giant planet, it's not just falling toward Jupiter under gravity, it's also moving sideways at tremendous speed, about 27 kilometers per second. This creates what physicists call a hyperbolic encounter, where the comet traces a curved path around Jupiter like a stone skipping off water. But here's where the magic happens. In our scenario, instead of the comet gaining energy and speed to escape our solar system faster, something different occurs. The precise angle of approach, modified by those tiny course corrections from outgassing, means 3IATLAS swings around Jupiter's far side and emerges traveling in almost the opposite direction. Think about it this way. Imagine you're spinning a ball on a string around your head, and suddenly you let go. The ball flies off in whatever direction it was heading at that exact moment. Jupiter's gravity works similarly, but instead of your hand providing the centripetal force, it's the immense gravitational field of a planet that contains more mass than all the other planets in our solar system combined. The numbers here are staggering. Jupiter's escape velocity is 59.5 kilometers per second. That means any object needs to be moving faster than that to break free from the planet's gravitational embrace. But 3IATLAS, in our scenario, doesn't quite reach that threshold. Instead, it gets caught in what astronomers call a capture orbit, swinging around Jupiter and being flung back toward the inner solar system. Now, let's talk about the timeline. If this gravitational redirect happened in March 2026, when would we start to see 3IATLAS heading back our way? This is where orbital mechanics becomes both beautiful and terrifying in its precision. The new trajectory would depend entirely on the exact details of the Jupiter encounter. But let's work with some realistic numbers based on what we know about the comet's current path and speed. After being redirected by Jupiter, 3IATLAS would likely take anywhere from 18 months to 3 years to complete its journey back toward Earth's vicinity. That might sound like a long time, but in astronomical terms, it's the blink of an eye. And here's something that should make you appreciate the incredible precision of celestial mechanics. We would know exactly where this comet is heading, down to the minute, years in advance. During those months of approach, 3IATLAS would become one of the most studied objects in the history of astronomy. Every major telescope on Earth and in space would be tracking its progress. We'd watch as this ancient messenger from another star system grows brighter and brighter in our skies, its characteristic wobbling jets becoming more active as it approaches the Sun once again. The European Space Agency's JUICE mission, which captured detailed images of 3IATLAS during its first pass through our solar system, would potentially be redirected for a second encounter. NASA might fast-track emergency missions to study this unprecedented opportunity to examine an interstellar object at close range, not just once, but twice. And that brings us to one of the most fascinating aspects of this entire scenario. 3IATLAS isn't just any interstellar visitor. Remember, this is a time capsule from the thick disk of our galaxy, formed when the universe was less than half its current age. The chemical analysis we've done shows it contains materials that simply don't exist in our local cosmic neighborhood. That 8:1 carbon dioxide to water ratio we talked about earlier. That tells us this comet formed in conditions so different from our solar system that it might as well be from an alien world. And in a very real sense, it is. The star system that gave birth to 3IATLAS might have been composed of elements forged in the very first generation of stars that lived and died before the materials that would become our Sun even existed. So in our hypothetical scenario, we're not just dealing with a comet redirected by Jupiter's gravity. We're dealing with the return of an ancient alien artifact, a messenger carrying information about the early universe encoded in its very atoms. Now, as 3IATLAS begins its return journey toward the inner solar system, something remarkable starts happening. This ancient comet, which has already given us more scientific surprises than any interstellar object in history, begins to wake up again. You see, comets are essentially dirty snowballs, and when they get closer to the Sun, they start to sublimate. That's a fancy way of saying the ice turns directly into gas without melting first, like dry ice on a hot day. But 3IATLAS isn't made of ordinary ice. Remember those impossible metals we detected? That atomic nickel vapor that shouldn't exist at the temperatures where we first observed it? As our redirected visitor approaches the Sun for a second time, those exotic chemical signatures become even more pronounced. The wobbling jets we observed during its first pass, those streams of gas and dust that rotate every 7 hours and 45 minutes, would intensify dramatically. But here's the kicker. We'd be watching this happen to material that formed in an entirely different stellar environment billions of years ago. Think about what that means for a moment. When our solar system was just a disk of dust and gas around a young star, 3IATLAS was already ancient, drifting through the galactic void. The atoms in its nucleus were forged in stellar furnaces that operated under different conditions, with different abundances of elements than anything in our cosmic neighborhood. The James Webb Space Telescope would have a field day. That 8:1 carbon dioxide to water ratio we detected, as the comet heats up again, we'd see how these alien ices behave under solar radiation. Would they sublimate at different rates than our local comets? Would new chemical compounds emerge that we've never seen before? And here's something that should absolutely blow your mind. The Very Large Telescope's detection of atomic nickel at impossible temperatures suggests there might be entirely unknown chemical processes happening within this interstellar visitor. Imagine discovering new physics, new chemistry, encoded in a comet that's older than our entire solar system. But let's talk about what you'd actually see if you stepped outside on a clear night during 3IATLAS's return approach. At first, absolutely nothing. The comet would be far too faint for naked eye observation, visible only to professional telescopes and advanced amateur equipment. But as weeks turn to months and the comet draws closer to the Sun, something magical begins to happen. That anti-tail we observed during its first visit, that bizarre spike of dust pointing directly toward the Sun, would reappear and grow. Unlike normal comet tails that stream away from the Sun like cosmic hair in a solar wind, this anti-tail defies our expectations. It's created by large dust grains left in the comet's orbital plane, and from Earth we see it edge on, creating this surreal effect of a tail pointing in the wrong direction. As 3IATLAS brightens, amateur astronomers around the world would start picking it up in their telescopes. Social media would explode with images of this returning visitor from deep space. And here's something beautiful to consider. Every photon of light reaching your eyes from this comet would have bounced off materials that haven't seen sunlight since the early universe was a fundamentally different place. The scientific community would be in overdrive. Emergency funding would pour into observational campaigns. Graduate students would dedicate their entire dissertations to analyzing the spectroscopic data. Because here's the thing about 3IATLAS that makes it so special. It's not just an interstellar visitor, it's a sample of the ancient galaxy delivered directly to our doorstep. When we talk about the thick disk of the Milky Way, where 3IATLAS likely originated, we're talking about a population of stars that formed 7 to 11 billion years ago when our galaxy was young and chaotic. These were stars born from gas clouds that contained fewer heavy elements than the stars we see today. The materials that condense to form 3IATLAS carry the chemical fingerprints of that ancient era. So as our hypothetical redirected comet approaches for its second close encounter with the Sun, we're not just watching a celestial light show. We're witnessing a cosmic archaeology expedition where the artifact has come to us instead of us having to dig for it. The international space agencies would be scrambling to position every available asset for optimal observations. The Hubble Space Telescope would track those wobbling jets in unprecedented detail. Radio telescopes would listen for any changes in the outgassing patterns. And somewhere, a new generation of scientists would be making discoveries that reshape our understanding of how planetary systems form and evolve throughout the galaxy. As 3IATLAS draws closer to the inner solar system in our hypothetical scenario, a crucial question emerges that would dominate headlines around the world. Just how close would this ancient visitor actually come to Earth? This is where the precision of orbital mechanics becomes absolutely critical. When astronomers calculate trajectories, they're not just making educated guesses. They're solving mathematical equations that describe how every massive object in the solar system influences every other object through gravitational interactions. It's like a cosmic ballet where every dancer affects every other dancer's movements. In our scenario, after 3IATLAS gets redirected by Jupiter, its new trajectory would depend on incredibly subtle factors. The exact angle of approach to Jupiter, the precise timing of the encounter, even the strength and direction of those wobbling jets we observed, all of these would combine to determine where our interstellar visitor ends up. Let's consider the most likely outcome based on the physics involved. A gravitational redirect by Jupiter would probably send 3IATLAS on an elliptical orbit that brings it much closer to the Sun than its original hyperbolic path. Instead of just passing through our solar system once, it would become temporarily captured, swinging around the Sun and potentially making multiple passes through the inner solar system. But here's something crucial that I want you to understand. Even in this hypothetical scenario, 3IATLAS would most likely maintain a safe distance from Earth. The same gravitational mechanics that could redirect the comet also tend to preserve stable separations between orbiting bodies. It's like the universe has built-in safety mechanisms. However, let's explore what would happen if our ancient visitor did come closer than expected. Say, within the orbit of the Moon, about 384,000 kilometers from Earth. At that distance, 3IATLAS would become visible to the naked eye for the first time since its discovery. Picture stepping outside on a clear night and seeing this messenger from another star system glowing softly in the constellation where it happens to be passing. You'd be looking at starlight reflected off materials that formed when the universe was a fundamentally different place. Those photons hitting your retina would carry information about stellar processes that occurred billions of years before Earth even existed. The scientific opportunities of such a close approach would be unprecedented. For the first time in human history, we'd have the chance to study pristine materials from another star system at close range. Every instrument we've developed for studying comets and asteroids would be focused on this single target. The European Southern Observatory's Very Large Telescope would map the surface composition of the nucleus in detail. NASA's Deep Space Network would track every subtle change in the comet's rotation and outgassing patterns. Amateur astronomers with backyard telescopes would contribute valuable observations to a global monitoring campaign. And here's something that gives me chills every time I think about it. If 3IATLAS came close enough, we might actually be able to see individual features on its surface. Those wobbling jets we've been tracking? We could watch them in real time, seeing how ancient ices sublimate under the warmth of our sun. The atomic nickel emissions that baffled scientists during the comet's first visit would become even more mysterious up close. How does a comet that formed in the cold outer reaches of an alien star system contain metals that vaporize at such low temperatures? The answer to that question could revolutionize our understanding of planetary formation throughout the galaxy. But let's talk about something even more profound. 3IATLAS carries within its nucleus a record of conditions in the early Milky Way. When this comet formed, our galaxy was a younger, more chaotic place. Star formation rates were higher, supernova explosions were more frequent, and the overall chemical composition of interstellar space was dramatically different. The high carbon dioxide content we detected tells us about the temperature and pressure conditions in that ancient stellar nursery. The unusual metal signatures hint at different nucleosynthesis processes occurring in those primordial stars. Every molecule we analyze from 3IATLAS is like reading a page from the universe's childhood diary. As our hypothetical close encounter approaches, something beautiful would happen to our perspective on Earth's place in the cosmos. We'd realize that we're not isolated inhabitants of a single star system. We're part of a galactic community connected through the migration of matter across vast distances and immense spans of time. The carbon atoms in your body right now were forged in stellar cores billions of years ago. The iron in your blood was created in supernova explosions that scattered heavy elements throughout the galaxy. And now 3IATLAS would be showing us that this cosmic recycling process operates on scales we're only beginning to comprehend. Now, as 3IATLAS continues its hypothetical approach toward Earth, space agencies around the world would be facing an unprecedented opportunity and challenge. How do you study an object that represents the single most important scientific discovery in human history? The answer would involve a coordinated international effort unlike anything we've ever attempted. NASA, the European Space Agency, the Japanese space program, even private companies like SpaceX, would pool their resources for what might be called the greatest scientific mission ever conceived. Imagine fast-tracking a spacecraft to rendezvous with 3IATLAS during its close approach. The engineering challenges would be immense, but the scientific payoff would justify moving heaven and earth to make it happen. We're talking about the first sample return mission from an interstellar object, the first direct analysis of materials from another star system. The spacecraft wouldn't need to land on the comet's surface. Given that 3IATLAS is actively outgassing, creating that spectacular coma of dust and vapor around its nucleus, a simple fly-through mission could collect pristine samples of this ancient material. Every grain of dust, Every molecule of gas would represent a time capsule from the early galaxy. But here's something that really gets my imagination going. What if we could actually see the surface features of 3I/ATLAS's nucleus up close? Those wobbling jets that rotate every 7 hours and 45 minutes suggest there are specific active regions on the comet's surface. What do those regions look like? Are they similar to the surface features we see on comets from our own solar system, or would they reveal entirely alien geological processes? The rotation period itself tells us something fascinating. 15.5 hours for a complete rotation means 3I/ATLAS is tumbling through space in a complex dance that's been going on for billions of years. Think about that. This chunk of ice and rock has been spinning in the cosmic dark since before our solar system existed, occasionally lit by the distant glow of alien suns as it wandered through interstellar space. During its close approach to Earth, we'd finally get to map the true shape and size of this interstellar wanderer. Current estimates put the nucleus somewhere between 440 meters and 5.6 kilometers in diameter. That's a huge range, and knowing the exact size would help us understand how much material 3I/ATLAS has lost during its journey through our solar system. The anti-tail phenomenon would become even more spectacular up close. Remember, this isn't a normal comet tail streaming away from the sun. It's a spike of large dust grains that creates an optical illusion, making it appear as though the tail is pointing directly toward the sun. From Earth's perspective, during a close approach, we might see this anti-tail stretching across several degrees of sky, a cosmic finger pointing back toward the comet's ancient origins. And speaking of origins, let's talk about what 3I/ATLAS's journey means for our understanding of how planetary systems interact across the galaxy. This comet didn't just randomly wander into our solar system. Its trajectory suggests it was ejected from its home system by gravitational interactions with planets or passing stars, then spent millions or billions of years drifting through the galactic void before encountering our sun's gravitational influence. That journey represents a form of natural panspermia, the idea that life or the building blocks of life could spread between star systems. While 3I/ATLAS itself isn't likely to contain living organisms, it does carry complex organic molecules that formed in an entirely different stellar environment. These molecules could tell us whether the basic chemistry of life is universal, or whether each star system develops its own unique molecular signatures. The implications for astrobiology would be staggering. If we found amino acids or other prebiotic molecules in 3I/ATLAS that were different from anything on Earth, it would suggest that the universe is even more biochemically diverse than we imagined. On the other hand, if we found familiar organic compounds, it would support the idea that certain molecular pathways are universal features of cosmic chemistry. But beyond the specific scientific discoveries, 3I/ATLAS's hypothetical return would represent something profound about humanity's relationship with the cosmos. For the first time in our species' history, we'd be directly interacting with materials from another star system. We'd be holding in our hands, analyzing in our laboratories, atoms that were forged in stellar furnaces that died before our sun was born. The psychological impact of that realization shouldn't be underestimated. Every human culture has looked up at the stars and wondered what lies beyond our local cosmic neighborhood. 3I/ATLAS would provide the first tangible answer to that ancient question. We are not alone in the universe, not because we found alien intelligence, but because we found alien matter, alien chemistry, alien geology. As 3I/ATLAS reaches its closest approach to Earth in our hypothetical scenario, something extraordinary would happen to our collective understanding of time and space. This ancient wanderer would become a bridge connecting us directly to the deep past of our galaxy. Let's put this in perspective. When 3I/ATLAS first condensed from the primordial disk around its parent star 7 to 11 billion years ago, the Milky Way looked completely different. Star formation was happening at a much more rapid pace. Massive stars were living fast and dying young in spectacular supernova explosions that enriched the interstellar medium with heavy elements. The spiral arms of our galaxy were still forming their characteristic structure. Earth didn't exist yet. Our sun was still billions of years away from igniting. The very atoms that would eventually become our planet were scattered across multiple star systems, waiting to be recycled through successive generations of stellar birth and death. And yet, 3IATLAS was already there, a silent witness to this cosmic evolution. During its close approach, every observation we make would be like reading chapters from the universe's autobiography. The isotope ratios in its ice would tell us about the nuclear processes occurring in those ancient stars. The dust grain composition would reveal how planetary formation worked in that primordial environment. Even the comet's internal structure would provide clues about how gravitational collapse and accretion operated in the early galaxy. But here's something that would capture the imagination of people around the world. As 3IATLAS swings past Earth, it would be moving at tremendous speed, probably around 30 to 40 kilometers per second relative to our planet. That means this messenger from deep space would cross our sky relatively quickly, visible for weeks or months rather than years. During that brief window, 3IATLAS would become the most photographed object in the solar system. Professional observatories would track its every movement, but so would millions of amateur astronomers and curious sky watchers. Social media would explode with images of this cosmic time traveler, each photograph capturing light that has bounced off materials older than our entire solar system. The educational impact would be transformative. Planetariums around the world would create special programs about 3IATLAS. Science museums would develop exhibits explaining interstellar objects and galactic evolution. A whole generation of students would grow up knowing that we live in a universe where matter regularly travels between star systems, carrying information about distant worlds and ancient times. And here's something beautiful to consider. The gravitational interaction that redirected 3IATLAS toward Earth would itself become a subject of intense scientific study. We'd have a real-time example of how planetary systems can capture and redirect interstellar objects, providing insights into how this process might work around other stars throughout the galaxy. The data we collect during 3IATLAS's close approach would keep scientists busy for decades. Every spectroscopic measurement, every image, every gravitational perturbation would need to be analyzed and understood. Graduate students would write dissertations on individual aspects of the comet's composition. Entire research careers would be built around understanding this single object. But beyond the immediate scientific impact, 3IATLAS would fundamentally change how we think about our place in the galactic community. We'd realize that interstellar space isn't empty. It's filled with wandering objects like 3IATLAS, refugees from distant star systems that carry with them the chemical signatures of alien worlds. Some of these interstellar visitors might even contain materials that formed around stars with different metallicities than our Sun. Stars that form from gas clouds with different abundances of heavy elements would produce planetary systems with unique chemical fingerprints. 3IATLAS gives us our first taste of this cosmic diversity. The philosophical implications would be profound. We'd have direct evidence that the universe operates as an interconnected system where matter, energy, and information flow freely between star systems across vast distances and immense spans of time. The boundaries between our solar system and their solar systems would start to seem artificial. As 3IATLAS begins to recede from Earth after its close approach, continuing on whatever new trajectory Jupiter's gravity has given it, we'd be left with a treasure trove of data and a fundamentally expanded perspective on cosmic evolution. This ancient comet would have shown us that we're not isolated inhabitants of a single star system, but participants in a galactic ecosystem that has been operating for billions of years. The samples collected during the flyby mission would become some of the most precious materials on Earth. Tiny grains of dust from 3IATLAS would be distributed to laboratories around the world, each fragment representing a direct connection to the early universe. Scientists would spend years analyzing these samples with every instrument we've developed for studying extraterrestrial materials. What are the actual risks involved when an interstellar object gets redirected toward our planet? This is where the precision of modern astronomy becomes absolutely crucial. Unlike the disaster movies where comets appear suddenly and threaten global catastrophe, real astronomical objects follow predictable paths governed by the laws of physics. We would know exactly where 3IATLAS is heading years in advance, down to the minute. The most likely scenario for our redirected comet would be a safe passage at a distance measured in millions of kilometers. Even if 3IATLAS came closer than originally predicted, say within the orbit of the Moon, it would still represent no immediate threat to Earth. Remember, this is a relatively small object, probably no more than 5 or 6 kilometers across, and it's not on a collision course. But let's explore what would happen if, in an extremely unlikely scenario, 3IATLAS did come close enough to enter Earth's atmosphere. This is where the physics becomes both fascinating and sobering. An object of this size moving at interstellar velocities would create an impact event unlike anything in recorded human history. However, and this is crucial, the same gravitational mechanics that could redirect 3IATLAS also make such a collision extremely improbable. The solar system is mostly empty space, and Earth represents a tiny target in the cosmic shooting gallery. The odds of a random interstellar object hitting our planet are astronomically small. What's more likely, and far more scientifically interesting, is that 3IATLAS would settle into a temporary orbit around the Sun, giving us multiple opportunities to study it over several years. This would be like having a permanent exhibition of alien geology right in our cosmic backyard. During these multiple passes through the inner solar system, we'd watch 3IATLAS evolve in real time. Each close approach to the Sun would activate those wobbling jets more intensely, stripping away layers of ancient ice and revealing deeper, more pristine materials underneath. It would be like watching an archaeological excavation happening in space. The changing activity patterns would tell us about the internal structure of this interstellar visitor. Is the nucleus homogeneous, made of the same materials throughout? Or does it have distinct layers that formed under different conditions? The answer would provide insights into how planetary formation worked in that ancient star system billions of years ago. And here's something that would absolutely revolutionize our understanding of comet science. 3IATLAS's unusual chemistry, that 8:1 carbon dioxide to water ratio, would allow us to study sublimation processes that simply don't occur with comets from our own solar system. We'd be observing alien physics in action. The atomic nickel emissions that baffled scientists during the comet's first visit would become even more mysterious during multiple close approaches. How does this metal vapor continue to appear at temperatures where it should be impossible? The answer might reveal entirely new chemical processes that operate under conditions we've never encountered before. But let's step back and consider the broader implications of having an interstellar object temporarily captured in our solar system. 3IATLAS would become a natural laboratory for studying how matter behaves when it's been exposed to the harsh environment of interstellar space for billions of years. Cosmic rays, those high-energy particles that stream through the galaxy, would have been bombarding 3IATLAS throughout its long journey. This radiation exposure would have altered the surface chemistry in ways we're only beginning to understand. Studying these changes would give us insights into the radiation environment between star systems. The comet's surface would also bear the scars of micrometeorite impacts accumulated over billions of years of wandering through space. Each tiny crater would represent a collision with interstellar dust grains, providing a record of the material density in different regions of the galaxy. As 3IATLAS continues its orbital dance around the Sun, something beautiful would happen to our perspective on cosmic time. We'd realize that this ancient object has been patiently waiting in the galactic dark for billions of years, carrying its cargo of primordial materials through the vast emptiness between stars, until finally encountering our solar system and being captured by Jupiter's gravity. The timing of this encounter would seem almost miraculous. 3IATLAS has been wandering through space since before Earth existed, and yet it arrives at our solar system at precisely the moment when humanity has developed the technology to study it properly. We have the telescopes to observe it, the spacecraft to visit it, and the scientific knowledge to understand what we're seeing. This cosmic coincidence would remind us that we live in a universe where matter, energy, and information are constantly flowing between star systems. The atoms in our bodies were forged in stellar cores and scattered by supernova explosions. The water in our oceans might have been delivered by comets similar to 3IATLAS billions of years ago. We are literally made of star stuff, and 3IATLAS would be showing us how that star stuff travels between worlds. As 3IATLAS settles into its hypothetical temporary orbit around our Sun, the scientific community would be grappling with discoveries that challenge everything we thought we knew about planetary formation and cosmic chemistry. Remember those impossible metal emissions we detected during the comet's first pass? The atomic nickel vapor appearing at temperatures where metals shouldn't sublimate? As 3IATLAS makes multiple approaches to the Sun, this mystery would deepen into one of the most significant puzzles in modern astronomy. The leading theory involves something called metal-carbonyl complexes. These are molecules where metal atoms are bound to carbon monoxide in ways that make them incredibly fragile. When ultraviolet light from the Sun hits these complexes, they break apart instantly, releasing pure metal vapor even in the freezing cold of space. But here's the kicker. We've never seen this process operating on such a massive scale in any comet from our own solar system. This suggests that 3IATLAS formed in a stellar environment with fundamentally different chemistry than our own. The star that gave birth to this ancient wanderer might have had unusual abundances of carbon and metals, creating conditions where these exotic molecular complexes could form naturally during planetary accretion. Think about what that means for our understanding of planetary diversity throughout the galaxy. If different star systems can produce such dramatically different chemical signatures, then the variety of worlds out there might be far greater than we ever imagined. 3IATLAS would be showing us that the universe is not just bigger than we thought, but weirder than we thought. The James Webb Space Telescope would be working overtime during 3IATLAS's extended stay in our solar system. Each orbital pass would provide new opportunities to study how these alien ices behave under solar heating. The telescope's incredible sensitivity would allow us to detect trace compounds that exist in concentrations too small to observe during a single flyby. And here's something that would capture the imagination of chemists around the world. 3IATLAS might contain organic molecules that formed under completely different conditions than anything on Earth. These wouldn't necessarily be signs of life, but they would represent alternative pathways for complex chemistry that we've never encountered before. The implications for astrobiology would be staggering. If life exists elsewhere in the universe, it might be based on chemical processes that are completely alien to terrestrial biology. 3IATLAS would give us our first glimpse into the molecular diversity that's possible when planets form around different types of stars. But let's talk about something even more profound. As 3IATLAS continues its orbital dance around our Sun, losing mass through sublimation with each close approach, it would be gradually revealing its internal structure. Like peeling an onion, each layer stripped away would expose materials that formed under slightly different conditions in that ancient stellar nursery. The innermost regions of the nucleus might contain the most pristine materials, ices that have been protected from cosmic radiation and interstellar weathering for billions of years. These would represent the closest thing we could get to a direct sample of the primordial disk around an alien star. Studying the layered structure of 3IATLAS would be like reading the geological history of another world. Each stratum would tell us about different phases of planetary formation in that distant system. Were there periods of intense bombardment by asteroids and comets? Did the parent star go through phases of variable brightness that affected ice formation? The answers would be written in the comet's internal architecture. As months turn to years, and 3IATLAS continues its extended visit to our solar system, something remarkable would happen to our understanding of galactic ecology. We'd realize that objects like this are probably common throughout the Milky Way, wandering between star systems and occasionally being captured by planetary systems like ours. This means that every star system in the galaxy is potentially connected to every other star system through the migration of these interstellar wanderers. Matter that formed around one star can end up orbiting another star millions of years later. The galaxy operates as a vast recycling system where materials are constantly being exchanged between different stellar neighborhoods. The philosophical implications would be profound. We'd have direct evidence that isolation is an illusion in the cosmic context. The boundaries between star systems are permeable. Matter, and potentially even life itself, can travel between worlds across vast distances and immense spans of time. 3IATLAS would become a symbol of this cosmic interconnectedness. Every time we look up at this ancient visitor in our night sky, we'd be reminded that we're part of a galactic community that has been operating for billions of years. The atoms in our bodies have traveled similar journeys, migrating from star to star, through the cosmic dark before eventually becoming part of our world. And here's something beautiful to consider. As 3IATLAS eventually exhausts its volatile materials and becomes inactive, it might settle into a permanent orbit around our Sun, becoming the first confirmed interstellar asteroid in our solar system. Future generations of humans would grow up knowing that we share our cosmic neighborhood with a permanent resident from another star system. Let's consider what this hypothetical scenario teaches us about the incredible interconnectedness of our universe and our place within the grand cosmic story. The most profound realization would be that we live in a galaxy where nothing exists in isolation. 3IATLAS represents just one example of how matter migrates between star systems, carrying with it the chemical fingerprints of distant worlds and ancient times. Right now, as you're listening to this, there are probably thousands of similar objects wandering through interstellar space, invisible messengers from alien solar systems. Some of these wanderers might be carrying materials even more exotic than what we've found in 3IATLAS. Imagine comets that formed around red dwarf stars where the habitable zones are so close to the parent star that water ice might never form. Or objects ejected from systems around massive blue giants where the intense radiation creates chemical processes we can barely imagine. The diversity of planetary systems throughout the galaxy means that each interstellar visitor carries unique information about how worlds form and evolve under different stellar conditions. 3IATLAS, with its ancient age and unusual chemistry, represents just the beginning of what we might discover as we detect more of these cosmic wanderers. And here's something that should fill you with wonder. The technology that allowed us to discover and study 3IATLAS didn't exist just a few decades ago. The ATLAS survey system that first spotted this interstellar visitor, the James Webb Space Telescope that revealed its alien chemistry, the sophisticated computer models that track its orbital mechanics, all of these represent the culmination of centuries of human curiosity and ingenuity. We are living through a golden age of astronomical discovery. Every year brings new revelations about the nature of our universe, from the detection of gravitational waves, to the imaging of black hole event horizons, to the discovery of thousands of exoplanets around other stars. 3IATLAS fits perfectly into this expanding picture of a universe that's far more dynamic and interconnected than we ever imagined. But beyond the specific scientific discoveries, 3IATLAS would represent something profound about the human spirit. Our species has always been driven by curiosity about what lies beyond the horizon. For most of human history, that horizon was limited to our own planet, then our own solar system. Now, for the first time, we're directly studying materials from another star system. This represents a fundamental expansion of human experience. We're no longer confined to wondering about alien worlds from a distance. We're actually holding pieces of those worlds in our hands, analyzing them in our laboratories, learning their secrets through the same scientific methods we use to understand our own cosmic neighborhood. The children growing up during 3IATLAS's extended visit to our solar system would have a fundamentally different perspective on the universe than any previous generation. They'd know from direct experience that we live in a galaxy where matter regularly travels between star systems. They'd understand viscerally that the elements in their bodies were forged in stellar cores and scattered by supernova explosions across vast distances and immense spans of time. This expanded cosmic perspective would inevitably influence how we think about our responsibilities as a species. If we're truly part of a galactic ecosystem where matter and energy flow freely between star systems, then our actions on Earth have implications that extend far beyond our own world. The way we treat our planet, the way we develop our technology, the way we prepare for our eventual expansion into space, all of these decisions become part of a much larger story. 3IATLAS would also remind us that the universe operates on timescales that dwarf human experience. This ancient comet has been wandering through space for 7 to 11 billion years, patiently carrying its cargo of primordial materials through the galactic dark. It survived the death of its parent star, the gravitational chaos of galactic evolution, and the harsh radiation environment of interstellar space, all to arrive at our solar system at precisely the moment when humanity has developed the ability to appreciate its significance. There's something almost poetic about that timing. The universe has been preparing this gift for us across billions of years, and we've been preparing ourselves to receive it across thousands of years of scientific development. The convergence of these two timelines represents one of the most remarkable coincidences in cosmic history. As 3IATLAS continues its orbital dance around our Sun, gradually losing mass and brightness with each close approach, it would be teaching us that everything in the universe is temporary. Stars are born and die, planets form and are destroyed. Even galaxies eventually merge and evolve. But the matter and energy that make up these cosmic structures are eternal, constantly being recycled into new forms and new configurations. We are part of this eternal cosmic recycling process. The atoms in our bodies have been part of countless other structures throughout the history of the universe. They've been inside stellar cores, scattered through interstellar space, incorporated into planets and moons and comets like 3IATLAS. And someday, billions of years from now, they'll be part of something else entirely. As 3IATLAS continues its extended residence in our solar system, the scientific discoveries would begin to reshape our fundamental understanding of how planetary systems evolve and interact across cosmic time. One of the most startling revelations would come from detailed analysis of the comet's rotation dynamics. Remember those wobbling jets that cycle every 7 hours and 45 minutes? As we observe 3IATLAS over multiple orbital periods, we'd notice something extraordinary. The wobble pattern is gradually changing. This isn't just random variation. The jets of gas and dust acting like tiny rocket engines are actually altering the comet's spin state in real time. We'd be watching a process that has been happening throughout 3IATLAS's billion-year journey through space, a slow but relentless evolution of its rotational dynamics driven by the sublimation of ancient ices. Think about what this means. Every time 3IATLAS encountered a star during its wandering through the galaxy, these same outgassing forces would have modified its rotation slightly. Over billions of years, this ancient comet has been tumbling through space in an ever-changing dance, its orientation and spin rate constantly evolving in response to stellar encounters. The implications for understanding other interstellar objects would be profound. We'd realize that these cosmic wanderers aren't just passive chunks of ice and rock drifting through space. They're dynamic systems that carry within their rotation states a record of every stellar encounter they've experienced during their galactic odyssey. But here's where the story gets even more fascinating. As 3IATLAS loses mass through sublimation, its gravitational field becomes weaker, and those wobbling jets become more effective at changing its rotation. We'd be watching this ancient object literally transform itself before our eyes, shedding not just material, but also angular momentum accumulated over billions of years. The European Space Agency's JUICE mission, originally designed to study Jupiter's moons, would become an unexpected hero in this story. The spacecraft's instruments, designed to analyze ice and organic compounds on Europa and Ganymede, would be perfectly suited to study 3IATLAS during its multiple passes through the inner solar system. JUICE would provide close-up images of the comet's surface that reveal details invisible from Earth-based telescopes. We'd see the actual source regions of those wobbling jets, the specific areas on the nucleus where ancient ices are sublimating and creating those spectacular gas plumes. Each active region would tell us about the internal structure and composition of this interstellar visitor. The surface mapping would reveal something extraordinary. 3IATLAS isn't uniform. Different regions of the nucleus would show different levels of activity, different chemical signatures, different responses to solar heating. This heterogeneity would tell us that the comet formed from materials that accreted under varying conditions in its parent stellar system. Some regions might be rich in carbon dioxide ice, creating those intense jets we've observed. Other areas might be dominated by water ice mixed with complex organic compounds. Still others might contain those mysterious metal-carbonyl complexes that produce the impossible nickel emissions. 3IATLAS would be revealed as a geological archive of its parent system's planetary formation process. As we map these different regions in detail, we'd begin to understand how planetary accretion worked in that ancient stellar environment. Did materials from different distances around the parent star get mixed together during the comet's formation? Were there distinct temperature and pressure zones that created the chemical diversity we're observing? The answers would revolutionize our understanding of how planetary systems form around different types of stars. The chemical gradients we observe in 3IATLAS would provide direct evidence of the conditions that existed in an alien stellar nursery billions of years ago. But perhaps the most profound discovery would come from analyzing the isotope ratios in different regions of the comet. Isotopes are versions of the same element with different numbers of neutrons, and their ratios provide fingerprints of the nuclear processes that created them. The isotope signatures in 3IATLAS would tell us about the types of stars that contributed material to its parent system. Were there nearby supernovae that enriched the local interstellar medium with heavy elements? Did asymptotic giant branch stars contribute unusual isotope ratios through their stellar winds? The comet's nucleus would contain a complete record of the stellar neighborhood where it formed. This isotopic archaeology would allow us to reconstruct the galactic environment that existed 7 to 11 billion years ago. We'd learn about star formation rates, supernova frequencies, and the overall chemical evolution of the Milky Way during its youth. 3IATLAS would become our most direct connection to the early history of our galaxy. As 3IATLAS continues its remarkable extended stay in our solar system, we'd begin to witness something that would fundamentally change our understanding of how interstellar objects behave when they encounter planetary systems. The gravitational influence of our solar system's planets wouldn't just affect 3IATLAS's orbit. It would also create subtle tidal forces that gradually reshape the comet's internal structure. Jupiter's massive gravitational field, the same force that redirected our ancient visitor in the first place, would continue to work on the comet during each orbital pass, slowly kneading and flexing its nucleus like cosmic hands working clay. These tidal forces would create internal stresses that could trigger new outgassing events from previously dormant regions of the comet. We might see jets suddenly appear from areas that had been inactive for millions of years, as Jupiter's gravity literally squeezes ancient pockets of volatile materials to the surface. This process would give us an unprecedented opportunity to study the three-dimensional structure of an interstellar object. Each new jet that appears would be like opening a window into a different layer of 3IATLAS's interior, revealing materials that formed under specific conditions in that distant stellar system billions of years ago. The Hubble Space Telescope would capture these changes in exquisite detail, creating time-lapse sequences that show how an ancient comet responds to the gravitational environment of an alien planetary system. We'd be watching geology in action on an object that predates our entire solar system. But here's something that would absolutely revolutionize our understanding of planetary formation. As 3IATLAS sheds material during its extended residence in our solar system, some of that ancient dust and gas would be captured by our own planet's gravitational fields. Imagine particles that formed around an alien star billions of years ago slowly spiraling down through Earth's atmosphere, eventually settling into our oceans and onto our continents. For the first time in our planet's history, Earth would be directly incorporating materials from another stellar system into its geological record. Future geologists studying sediment cores from this period would find layers containing isotope signatures that don't match anything else in Earth's geological history. These alien materials would become permanent markers in our planet's rock record, evidence of the time when an interstellar visitor shared our cosmic neighborhood. The atmospheric entry of 3IATLAS particles would create spectacular meteor showers, unlike anything ever observed. These wouldn't be ordinary shooting stars created by debris from our own solar system. They'd be cosmic fireworks powered by materials that witnessed the birth and death of alien worlds. Amateur astronomers around the world would organize viewing parties to watch these interstellar meteors streak across our skies. Each bright flash would represent the final moment of a dust grain's billion-year journey through space, a tiny piece of cosmic history burning up in our atmosphere and adding its atoms to our world. The scientific value of collecting these particles would be immense. Specialized aircraft would fly through the upper atmosphere, using aerogel collectors to capture intact grains of interstellar dust. These samples would provide the most pristine materials from another star system that we've ever obtained. Laboratory analysis of these particles would reveal details about 3IATLAS's composition that we could never obtain through remote observation. We'd be able to study individual mineral grains under electron microscopes, map their crystal structures, and analyze their chemical composition with unprecedented precision. Some of these grains might contain presolar materials, tiny crystals that formed in the atmospheres of dying stars before being incorporated into 3IATLAS's parent system. These would be among the oldest solid materials in the universe, time capsules from the very first generation of stars that enriched the galaxy with heavy elements. The discovery of presolar grains in 3IATLAS would provide direct evidence of how stellar nucleosynthesis worked in the early universe. We'd be holding in our hands materials that witness the cosmic processes that created the elements necessary for planets and life. As 3IATLAS continues to evolve during its extended visit, we'd also observe how its coma and tail structures change in response to varying solar radiation. The comet's distance from the Sun would oscillate with each orbit, creating a natural laboratory for studying how interstellar ices respond to different levels of stellar heating. During close approaches to the Sun, 3IATLAS would develop an enormous coma that could span millions of kilometers. This vast cloud of gas and dust would contain materials that haven't been exposed to stellar radiation since the comet's formation billions of years ago. We'd be watching the sublimation of primordial ices in real time. The spectroscopic analysis of this expanding coma would reveal new molecular species that we've never detected in solar system comets. These exotic compounds would tell us about chemical processes that operated in the early universe under conditions very different from those in our local stellar neighborhood. The tail dynamics would be equally fascinating. As 3IATLAS swings around the Sun, solar wind pressure would sculpt its tail into complex shapes that depend on the comet's orientation and the strength of the solar magnetic field. We'd see how interstellar materials interact with our Sun's particle environment. The complex organic molecules that we've detected in 3IATLAS's coma aren't just scientifically interesting. They represent potential building blocks for biological processes that could operate under conditions completely different from those on Earth. These molecules, formed in an alien stellar environment, were preserved in the deep freeze of interstellar space for billions of years, and are now being released into our solar system. Some of these organic compounds might be amino acids, the fundamental components of proteins. Others could be nucleotide bases, the building blocks of DNA and RNA. If we found these biological precursors in 3IATLAS, it would provide the strongest evidence yet that the chemistry of life might be universal throughout the galaxy. But here's where the implications become truly mind-bending. If 3IATLAS contains organic molecules that could contribute to biological processes, and if similar interstellar objects have been visiting planetary systems throughout galactic history, then life itself might be a collaborative effort between different star systems. The organic compounds that eventually led to life on Earth might not have originated entirely in our own solar system. Some of them could have arrived aboard ancient interstellar visitors like 3IATLAS, carrying genetic information or chemical templates from worlds that orbited distant stars billions of years ago. This wouldn't be life as we typically imagine it, with little green beings traveling between stars in spacecraft. Instead, it would be life as a galactic phenomenon, where the basic chemistry of biology spreads naturally between star systems through the migration of objects like 3IATLAS. The implications for astrobiology would be revolutionary. Instead of asking whether life exists elsewhere in the universe, we'd be asking how the chemistry of life has been shared between different worlds throughout cosmic history. We might discover that all life in the galaxy shares common molecular ancestors that have been traveling between star systems for billions of years. As 3IATLAS continues its extended residence in our solar system, we'd have the unprecedented opportunity to study this process in real time. We'd watch as organic molecules that formed around an alien star billions of years ago are released into the space around our own star, potentially contributing to the chemical environment that future life forms might encounter. The educational impact of these discoveries would transform how we teach biology and chemistry. Students would learn that the molecules in their own bodies might have cosmic origins, that the DNA in their cells could contain information that has been traveling between star systems since the early universe. This expanded perspective would fundamentally change how we think about our place in the cosmic story. We wouldn't just be inhabitants of Earth, or even citizens of the solar system. We'd be participants in a galactic ecosystem where matter, energy, and potentially even information flow freely between different worlds across vast distances and immense spans of time. The philosophical implications would be profound. If life is truly a galactic phenomenon, then our responsibilities extend far beyond our own planet. The way we develop our technology, the way we prepare for our eventual expansion into space, the way we search for life elsewhere in the universe, all of these activities become part of a much larger story that connects us to every other world in the galaxy. 3IATLAS would also teach us about the incredible patience of cosmic processes. This ancient comet has been carrying its cargo of organic molecules through the galactic dark for 7 to 11 billion years, waiting for the right moment to release them into a planetary system where they might contribute to the chemistry of life. The timing of its arrival at our solar system, just as humanity has developed the technology to study it properly, would seem almost miraculous. But perhaps it's not a coincidence at all. Perhaps the universe has been preparing for this moment across billions of years, orchestrating the complex dance of stellar evolution, planetary formation, and biological development that has led to this unprecedented encounter. As we continue to study 3IATLAS during its extended visit, we begin to see patterns in its behavior that reveal the deep connections between cosmic chemistry and biological processes. The same forces that created the organic molecules in this ancient comet are still operating throughout the galaxy, continuously seeding new star systems with the chemical building blocks of life. The data we collect from 3IATLAS would become the foundation for entirely new fields of science. Galactic biology would emerge as a discipline that studies how life develops and spreads throughout the Milky Way. Cosmic chemistry would investigate how molecular complexity evolves in different stellar environments. These new sciences would require international collaboration on an unprecedented scale. The discoveries emerging from 3IATLAS would be too important and too complex for any single nation or institution to handle alone. We'd need to pool our resources, share our data, and work together as a species to understand the implications of what we're learning. The children growing up during this period would have access to educational opportunities that previous generations could never have imagined. They'd be able to study actual samples of interstellar materials in their chemistry classes, analyze real data from alien star systems in their astronomy courses, and participate in research projects that are literally expanding the boundaries of human knowledge. A dormant 3IATLAS would present an irresistible target for a dedicated space mission. Without the complications of active outgassing and a surrounding coma, a spacecraft could approach the nucleus safely and conduct detailed surface mapping, sample collection, and even attempt a landing. Imagine the first human-made object to touch the surface of a world that formed around another star. The engineering challenges would be immense, but the scientific payoff would justify any expense. We'd finally be able to drill into the nucleus and extract core samples that reveal the complete history of this ancient wanderer. The surface composition mapping would reveal details that we could never obtain through remote observation. We'd see how billions of years of cosmic ray bombardment have altered the outer layers of the nucleus. We'd map the distribution of different ice types and organic compounds across the surface. We'd identify the exact source regions of those wobbling jets that captivated us during the comet's active phase. But perhaps most importantly, we'd be able to search for the most complex organic molecules that 3IATLAS has to offer. Deep within its nucleus, protected from cosmic radiation and stellar heating, there might be molecular structures of incredible complexity that formed in the primordial disk around an alien star. These molecules could include amino acid chains, nucleotide sequences, or even more exotic organic polymers that we've never encountered before. If we found evidence of molecular self-organization or chemical processes that approach the threshold of biological activity, it would revolutionize our understanding of how life emerges in the universe. The discovery of such complex chemistry in 3IATLAS would suggest that the transition from non-living matter to living systems might be a natural consequence of cosmic evolution. The same processes that create stars and planets might also create the molecular complexity necessary for life to emerge. As 3IATLAS settles into its new role as our solar system's first interstellar asteroid, it would become a permanent reminder of our connection to the broader galactic community. Future generations of humans would grow up knowing that we share our cosmic neighborhood with a permanent resident from another star system. The educational value would be immeasurable. School children would learn about galactic evolution by studying an actual piece of the ancient Milky Way. University students would conduct research projects using data collected from an object that predates our entire solar system. The scientific papers published about 3IATLAS would fill entire libraries. But beyond the immediate scientific impact, the presence of 3IATLAS in our solar system would fundamentally change how we think about space exploration and our future as a spacefaring species. We'd have direct evidence that interstellar travel is not only possible but happens naturally throughout the galaxy. The same gravitational processes that captured 3IATLAS could potentially be used to redirect human spacecraft toward other star systems. We'd begin to see interstellar space not as an impossible barrier, but as a navigable ocean where matter and energy flow freely between different worlds. The long-term presence of 3IATLAS would also influence how we design our own interstellar missions. We'd learn from studying how this ancient object survived billions of years in the harsh environment between stars. The materials science insights gained from analyzing its nucleus could inform the construction of spacecraft designed to make similar journeys. As we develop the technology for interstellar exploration, 3IATLAS would serve as both inspiration and practical guide. It would remind us that we're not the first travelers to cross the vast distances between stars, and it would teach us how to build vehicles capable of surviving such epic journeys. The presence of this ancient wanderer in our solar system would mark the beginning of humanity's transition from a single-planet species to active participants in the galactic community. We'd no longer be isolated observers of the cosmic drama unfolding around us. We'd be direct participants in the ancient process of matter and information exchange between star systems. The presence of 3IATLAS in our solar system would mark a turning point in human consciousness. For the first time in our species' history, we would have tangible proof that we live in a universe where worlds are connected across vast distances and immense spans of time. This wouldn't be theoretical knowledge gleaned from textbooks or computer simulations. It would be direct, visceral experience of holding alien matter in our hands. The psychological impact of this realization would ripple through every aspect of human culture. Artists would create works inspired by the knowledge that we share our cosmic neighborhood with materials from another star system. Musicians would compose symphonies that capture the wonder of billion-year journeys through interstellar space. Writers would craft stories that explore what it means to be part of a galactic community, but perhaps the most profound impact would be on how we raise and educate the next generation. Children born during 3IATLAS's extended visit would grow up with a fundamentally different relationship to the universe than any previous generation of humans. They would know from direct experience that the cosmos is not a collection of isolated islands, but an interconnected web where matter, energy, and information flow freely between different worlds. These children would ask different questions than we do. Instead of wondering whether life exists elsewhere in the universe, they would ask how life spreads between star systems. Instead of seeing space as an empty void that separates worlds, they would understand it as a medium through which cosmic evolution operates on galactic scales. The educational curricula would be revolutionized. Astronomy classes would include hands-on analysis of actual interstellar materials. Chemistry courses would explore how molecular complexity develops under different stellar conditions. Biology classes would investigate how the building blocks of life might be shared between worlds across cosmic distances. The research opportunities would be unprecedented. Graduate students would have access to samples from another star system for their dissertation projects. Postdoctoral researchers would spend their careers analyzing data that reveals how planetary formation worked in the early galaxy. Senior scientists would collaborate on international projects that literally expand the boundaries of human knowledge. The technological innovations driven by 3IATLAS research would transform our capabilities in ways we can barely imagine. New analytical instruments developed to study interstellar materials would find applications in medicine, environmental science, and materials engineering. The computational models created to understand the comet's billion-year journey would advance our understanding of complex systems throughout science and technology. The international cooperation required to study 3IATLAS properly would create new models for how humanity can work together on challenges that transcend national boundaries. The data-sharing protocols, the collaborative research frameworks, the joint mission planning processes, all of these would establish precedents for future global scientific endeavors. As 3IATLAS gradually transitions from active comet to dormant asteroid, it would become a permanent fixture in our solar system's architecture. Future space missions would use it as a way station for interstellar exploration, a place where we can study the effects of billion-year journeys through space before attempting such journeys ourselves. The asteroid that 3IATLAS becomes would serve as humanity's first interstellar embassy, a piece of alien real estate that we can visit, study, and eventually inhabit. The first human outpost on an interstellar object would represent a symbolic milestone in our species' expansion beyond our home star system. The scientific discoveries emerging from 3IATLAS would continue for decades, possibly centuries. Each new analytical technique we develop would reveal additional layers of information encoded in its ancient materials. Each new theoretical framework we construct would provide fresh insights into how this cosmic wanderer fits into the broader story of galactic evolution. The philosophical implications would continue to evolve as well. The knowledge that we live in a universe where matter regularly travels between star systems would influence how we think about identity, belonging, and our responsibilities as cosmic citizens. We would begin to see ourselves not just as inhabitants of Earth or even the solar system, but as temporary custodians of materials that have been part of the galactic recycling process for billions of years. The religious and spiritual communities would grapple with the implications of 3IATLAS in their own ways. Some would see it as evidence of divine design operating on cosmic scales. Others would interpret it as confirmation that the universe itself is sacred, that every atom carries within it the history of stellar birth and death across immense spans of time. The economic implications would be substantial as well. The technologies developed to study 3IATLAS would create new industries. The international collaborations would establish new trade relationships. The educational opportunities would produce a generation of scientists and engineers with unprecedented expertise in interstellar science. As we look toward the future, 3IATLAS would serve as both inspiration and practical guide for humanity's eventual expansion into interstellar space. We would learn from its billion-year journey how to design spacecraft capable of surviving the harsh environment between stars. We would understand from its chemical composition what resources might be available in other stellar systems. Most importantly, 3IATLAS would teach us that we are not alone in the universe, not because we have found alien intelligence, but because we have found alien matter, alien chemistry, alien geology. We would know with absolute certainty that the processes that created our world operate throughout the galaxy, that the elements in our bodies have cosmic origins, that we are literally made of star stuff that has been traveling between worlds since the early universe. Have you ever wondered what will happen when Andromeda collides with the Milky Way? In this video, we explore the science behind the most spectacular galactic event in our future, the Milky Way-Andromeda collision. It's a must-watch.